There exists a profound disconnect between what Saturn's moon Mimas appears to be and what it actually conceals beneath its frozen surface. When you examine the raw imagery transmitted back from deep space, this celestial body presents itself as the very archetype of geological death. The coloration is uniformly gray, the terrain is saturated with impact craters, and the entire mass is locked in perpetual ice. There are no visible indicators of internal activity whatsoever. No fracture systems snake across the landscape. No cryovolcanic plumes erupt from hidden vents, and no tectonic boundaries suggest crustal movement. From a purely visual standpoint, Mimas has achieved notoriety for a single distinctive characteristic: its eerie similarity to the fictional Death Star from cinematic history. The lunar surface is utterly dominated by Herschel crater, an enormous impact depression that consumes approximately 1/3 of the moon's visible hemisphere. This geological scar, christened in honor of William Herschel, who first documented this moon's existence, bestows upon Mimas an inexplicable quality that borders on the manufactured. The appearance evokes comparisons not to naturally formed astronomical objects, but rather to engineered constructions, or perhaps the remnants of some colossal artificial structure abandoned in planetary orbit. This scarred, seemingly inert appearance led the astronomical community to spend multiple decades categorizing Mimas as nothing more than a geological relic. The prevailing assumption held that this object represented little beyond a monolithic block of frozen water that had remained fundamentally unchanged across billions of years of cosmic history. Such conclusions appeared entirely reasonable given the available evidence. When scientists pursued their investigations into potential locations harboring liquid water or perhaps even biological activity, their attention naturally gravitated toward moons exhibiting obvious surface dynamism. Bodies like Enceladus and Europa, which demonstrably expel water and ice particles directly into the surrounding vacuum, became the primary focus of astrobiological interest. Mimas was systematically overlooked in these searches. Its surface appeared excessively damaged and insufficiently active to warrant serious consideration as a harbor for anything scientifically valuable. The working hypothesis suggested that the ice shell was simply too thick and the impact history too catastrophic to permit the existence of any subsurface features worth investigating. This assessment, however, has been comprehensively invalidated by recent analytical work. Contemporary data processing techniques applied to archival information from the Cassini mission, spearheaded by planetary scientist Valery Laney and his collaborative research team, have definitively established that Mimas is absolutely not a homogeneous frozen mass extending from surface to core. Contrary to the implications of its weapon-like exterior morphology, the internal structure remains geologically active in ways that completely escape detection for generations. More specifically, this moon that appears so thoroughly artificial is currently concealing a planet-wide liquid water ocean, situated approximately 20 to 30 kilometers beneath its protective ice shell. While scientific teams have explored alternative hypothetical frameworks to account for the observational data, current computational models converge most strongly on the subsurface ocean interpretation as the explanation most consistent with all available measurements. This revelation fundamentally dismantles the conventional framework we have historically employed to identify potentially habitable environments. The object we are examining is not a lifeless chunk of frozen material drifting through space. Instead, we find ourselves confronting what may be classified as a covert ocean world, one that has successfully disguised itself as unremarkable cosmic debris for the entirety of human observation. The story of how this discovery emerged begins in the year 2010, when the Cassini spacecraft executed a close approach maneuver past Mimas with the objective of generating detailed thermal maps of the lunar surface. The scientific team orchestrating this observational campaign was not anticipating any particularly unusual findings during the mapping sequence. The prediction models were straightforward and aligned with standard thermal behavior for airless planetary bodies. Scientists anticipated that surface temperatures would reach their maximum values near the equatorial regions during local early afternoon hours, then exhibit a smooth, gradual decline as measurements moved toward polar latitudes or transitioned into the night hemisphere. The expected thermal signature should have manifested as a gentle, continuous gradient of heat distribution. The actual data transmitted back to Earth by Cassini's composite infrared spectrometer told an entirely different story. Rather than displaying the anticipated smooth thermal transition, the heat distribution map revealed a configuration characterized by sharp boundaries and dramatic contrast. The region exhibiting elevated temperatures was configured in a shape that perfectly replicated the iconic 1980s video game character Pac-Man. This thermal pattern appeared to be consuming the Herschel crater itself, generating a visual presentation so bizarre that it initially produced genuine confusion among the mission scientists attempting to interpret the findings. This thermal anomaly existed because the surface composition of Mimas demonstrates significant regional variation. The Pac-Man configuration represents a stark differentiation in surface material properties. The warmer zones rendered in yellow and red coloration on the thermal maps correspond to surface areas that retain absorbed thermal energy with high efficiency. Conversely, the cooler regions depicted in blue tones dissipate heat almost instantaneously upon entering shadow. This physical characteristic is quantified through a parameter known as thermal inertia. Terrestrial experience provides useful analogies for understanding thermal inertia. Materials such as concrete or solid rock maintain elevated temperatures for extended periods following sunset. Sand, by contrast, releases accumulated heat very rapidly once direct solar illumination ceases. Mimas exhibited what can only be described as a bifurcated thermal personality. The hemisphere that faces forward in the Moon's orbital direction behaves thermally like consolidated rock, maintaining absorbed heat over time. The remaining surface regions behave more like loosely packed powder, shedding thermal energy at extreme rates the instant they rotate away from direct sunlight. The mechanism generating this textural dichotomy adds yet another layer of peculiarity to this already enigmatic moon. As Mimas follows its orbital path around Saturn, the leading hemisphere continuously plows through an environment saturated with high-energy electrons trapped within Saturn's powerful magnetosphere. These energetic particles relentlessly bombard the ice crystals on the forward-facing surface, effectively fusing the previously powdery granules into solid, consolidated ice blocks. This radiation-induced transformation hardens the impacted surface and dramatically elevates its thermal inertia. The trailing hemisphere, shielded from this electron bombardment by the Moon's own bulk, retains its loose, powdery consistency. This process creates an extraordinarily sharp thermal and textural boundary across the lunar surface, one that remains completely invisible to optical imaging systems, but becomes glaringly obvious when examined through thermal infrared instruments. The discovery reinforced the existing perception that Mimas represented a heavily weathered object that had endured battering not merely from asteroid impacts, but from the invisible radiation environment generated by its parent planet. Prior to the ocean discovery, this thermal signature was cataloged as merely another curiosity that seemed to confirm Mimas as a frozen, battered remnant rather than a dynamically evolving world. The thermal patterns highlighted a surface that had been subjected to intense external forces operating continuously across billions of years, effectively distracting the scientific community from investigating what might lie concealed in the deep interior. The Herschel crater stands as the defining morphological feature of Mimas. This is not simply a surface blemish or minor impact scar. Rather, it represents a permanent physical record of a collision event that came perilously close to completely destroying the Moon itself. The crater extends roughly 130 kilometers in diameter. The diameter of Mimas itself measures only approximately 400 kilometers. This geometric relationship means that the crater dominates a full third of the visible hemisphere. To properly contextualize the scale of violence this impact represents, one must translate the proportions to terrestrial dimensions. If a proportionally similar impact had occurred on Earth, the resulting crater would exceed the total land area of the Australian continent. The impact energy was so extraordinarily violent that the physics of the collision event remain visibly recorded across the entire global surface. When the impacting asteroid struck, it did not simply excavate surface material and create a depression. The collision generated massive seismic shock waves that propagated through the entire internal volume of the Moon. These compression waves raced through the center of Mimas and converged with focused intensity at the precise location directly opposite the impact site. This geometrically opposite point is termed the antipodal region in planetary geology. At that antipodal location, the surface structure is catastrophically disrupted. The terrain is buckled and fragmented into systems of deep canyons and fracture networks known as chasmata. This antipodal damage was generated exclusively by the concentrated seismic energy from the Herschel impact as it passed through the Moon's interior and explosively deformed the crust from beneath at the convergence point. This damage pattern creates a picture of a world that has been structurally compromised throughout its entire volume. The architectural details of the crater itself are immense by any measure. The crater walls rise approximately 5 kilometers in height, while the excavated floor plunges 10 kilometers below the surrounding terrain. At the geometric center of the depression stands a massive central peak rising 6 kilometers above the crater floor, formed through the instantaneous elastic rebound of crustal material immediately following the impact event. This geological structure remains preserved in pristine condition because Mimas possesses no atmosphere capable of generating wind erosion or weather-driven degradation processes. For multiple decades, this extensive structural damage actively supported the theoretical framework proposing that Mimas was composed of solid ice throughout its entire volume. A subsurface liquid ocean typically functions to dampen and dissipate seismic shock waves because fluid materials absorb and redistribute impact energy through fundamentally different physical mechanisms than solid materials. The documented fact that shock waves from the Herschel impact propagated with such extraordinary efficiency through the Moon's interior strongly suggested that Mimas was frozen completely solid, extending from surface to core at the time the impact occurred. This observation introduces an additional layer of complexity to the recent oceanographic discovery. The evidence pattern suggests that Mimas was very likely a completely frozen body when the Herschel impact event took place. The liquid water ocean we can now detect through orbital mechanics represents a more recent development in the Moon's geological history, one that emerged and evolved only after this near-catastrophic collision event. The Herschel crater left Mimas appearing as a battered, static shell of ice, continuously reinforcing the scientific consensus that classified it as a dead object suspended in the vacuum of space. The discovery that Mimas harbors an internal ocean was not achieved through analysis of surface photography or visual imagery. Instead, the breakthrough emerged from meticulous analysis of the precise rotational dynamics exhibited by the Moon. Astronomers utilized data archives from the Cassini spacecraft to track the rotation of Mimas with extreme measurement precision. They focused their attention on specific, identifiable crater features on the surface and measured the geometric positions of these landmarks across extended time periods to determine whether the Moon's rotation maintained perfect stability. The rotation was definitively not stable. Mimas exhibits a particular type of rotational motion classified as libration. This manifests as a subtle oscillation or wobbling behavior that occurs throughout the Moon's orbital cycle around Saturn. Because Mimas follows a slightly elliptical rather than perfectly circular orbit, its orbital velocity varies as it moves closer to and then farther from the planet. This variation in orbital speed induces the Moon to rock gently back and forth around its rotational axis. Every moon following an elliptical orbital path experiences this phenomenon to some measurable degree. The magnitude of the libration wobble is determined entirely by the internal mass distribution and structural configuration of the object. When scientists calculated the theoretically expected libration amplitude for Mimas, they utilized a computational model representing a homogeneous sphere composed of ice and rock. Based on the measured total mass and physical dimensions of the Moon, fundamental physics establishes a quantitative limit on how much a completely solid object can wobble. The gravitational influence of Saturn acts upon the Moon's mass distribution to maintain relative rotational stability. If Mimas were indeed solid throughout, the mechanical connection between the outer crust and the deep interior core would be completely rigid. The entire object would be forced to move as a single unified mass, which requires substantial energy input. This rigid coupling would necessarily keep the libration wobble small and subtle. The observational data returned from Cassini instruments revealed a libration amplitude that was physically impossible for a solid object to produce. Mimas was rocking back and forth with approximately twice the amplitude that theoretical models predicted for a solid body. This magnitude of rotational motion indicated unambiguously that the outer ice shell was not rigidly mechanically coupled to the dense interior core. The only viable explanation for such an exaggerated oscillation amplitude is that the icy crust has become physically decoupled from the interior structure. This decoupling creates a scenario where the outer shell possesses freedom to slide around independently of the core. For the shell to slide with minimal resistance, it must be floating on some intermediate layer. This requires a lubrication layer that eliminates frictional coupling between the ice shell and the underlying rock. In planetary science, the only material capable of existing in this role under the temperature and pressure conditions present is liquid water. This rotational motion provided what scientists describe as smoking gun evidence. It definitively proved that the ice shell undergoes decoupling from the core and slips laterally over a global ocean layer. The libration signature represents the physical manifestation of a hidden liquid layer that permits the surface to move with substantially greater freedom than any solid rock structure could ever exhibit. The confirmed existence of a liquid water ocean inside Mimas presents a significant challenge to standard planetary physics. Mimas qualifies as a very small object by planetary standards. In planetary thermal evolution theory, small bodies cool toward equilibrium very rapidly. Any residual heat remaining from the Moon's formation process billions of years in the past should have radiated away into space long ago. According to all standard thermal evolution calculations, Mimas should exist as a cold, geologically dead, frozen mass. For water to persist in liquid phase, there must be an active ongoing power source continuously generating thermal energy to prevent the water from freezing solid. The source of this sustained energy input is gravitational in nature. Mimas does not orbit Saturn along a perfect circular path. Instead, its trajectory follows a slightly elliptical configuration, meaning the orbit possesses measurable eccentricity. During each complete revolution around the planet, the Moon approaches closer to Saturn and subsequently drifts to greater distances. This continuous variation in orbital separation creates a dynamically changing gravitational environment. When Mimas reaches its closest orbital approach to Saturn, the immense gravitational field of the gas giant exerts tremendous force on the Moon. This gravitational stress physically stretches Mimas into a slightly elongated oblate configuration. When Mimas moves to the more distant portion of its orbital path, the gravitational stress diminishes and the Moon rebounds toward a more spherical equilibrium shape. This cyclical deformation sequence repeats during every single orbital period. This continuous process of stretching and relaxing is termed tidal flexing in planetary science. It operates as a mechanical process that functions essentially like repeatedly bending a metal wire back and forth at the same location. If you flex a wire through many cycles, the material at the flexure point generates heat. This thermal production results from internal friction between atomic structures. An identical physical process occurs within the interior of Mimas. The rock and ice composing the internal structure undergo grinding and shearing as the Moon cyclically changes shape. This internal friction generates a substantial quantity of thermal energy. Because the heat generation occurs deep within the Moon's interior, the thermal energy radiates outward from the core region. This heat flux melts the lowermost layers of the overlying ice shell. Across timescales of millions of years, this process has carved out a global reservoir of liquid water situated between the rocky core and the frozen ice crust. What distinguishes Mimas as unique is the manner in which it manages this internally generated heat. On a moon such as Enceladus, the tidal heating operates at such intensity that it fractures the ice shell and vents thermal energy into space through dramatic cryovolcanic geysers. On Mimas, the heating regime operates more subtly. The heat generation is sufficient to achieve ice melting, but insufficiently violent to fracture through the thick protective outer shell. The approximately 30-kilometer thick ice crust functions as a massive thermal insulation blanket. It traps the generated heat within the Moon's interior, allowing the ocean to exist and persist without betraying any thermal signatures detectable at the surface. The system operates as a perfectly sealed thermal environment, continuously powered by the gravitational interaction with Saturn. In the comprehensive study of Saturn's satellite system, Enceladus has consistently occupied the position of the gold standard exemplar for ocean-bearing worlds. It functions effectively as the conspicuous neighbor in the planetary system. This moon announces its presence through the most unambiguous methods imaginable. Enceladus propels massive plumes composed of water, vapor, and ice particles, hundreds of kilometers into the surrounding space, from fracture systems concentrated at its south polar region. These cryovolcanic geysers operate with such extraordinary power that they actually supply material that populates one of Saturn's distinctive ring structures. Due to this spectacular visible activity, the scientific community has possessed knowledge about the subsurface ocean on Enceladus almost since the moment the Cassini spacecraft first arrived in the Saturnian system. The evidence was visual, dramatic, and completely undeniable to any observer. Mimas represents the precise opposite terminus of the spectrum of ocean world manifestations. It qualifies as what might be termed a stealth ocean world. Despite orbiting within the same planetary system and experiencing fundamentally similar gravitational forcing mechanisms, Mimas maintains its secrets in complete containment. The moon does not exhibit tiger stripe fracture patterns or fissures actively venting material into space. It does not continuously resurface itself with deposits of fresh crystalline ice, as Enceladus demonstrably does. Instead, Mimas preserves a heavily cratered ancient surface that projects the appearance of complete geological death. The fundamental difference between these two ocean-bearing moons lies in the thickness characteristics of their respective ice shells. On Enceladus, the ice crust overlying the south polar region can measure as thin as 1 to 5 kilometers in depth. This represents a sufficiently thin barrier that internal pressure from the subsurface ocean can breach through and vent material directly into the vacuum environment. Mimas, however, possesses a substantially more massive containment structure. The ice shell encasing Mimas is estimated through gravitational modeling to measure between 20 and 30 kilometers in thickness. This constitutes a massive, heavy lid that effectively suppresses any potential surface expression of internal activity. The pressure exerted by the ocean layer below remains insufficient to crack through such a dense and extensive ice barrier. This thickness differential explains precisely why Mimas successfully deceived astronomical observers for such an extended duration. The scientific community spent multiple decades operating under a specific observational bias in the search for extraterrestrial oceans and potential life. We systematically searched for surface signals and manifestations of internal activity. The working assumption held that if a moon harbored a subsurface ocean, it would necessarily display some indication of that ocean on its exterior surface. We searched for smooth terrain, tectonic fracture systems, or active plume eruptions. Mimas exhibits precisely none of these expected indicators. It is proven definitively that a global liquid water ocean can be concealed completely and effectively beneath a heavily battered, ancient-appearing surface. This comparison between Enceladus and Mimas forces a fundamental reevaluation of how planetary scientists categorize and prioritize satellite bodies. Enceladus is quite likely the exceptional case rather than the representative norm. It remains relatively rare for a moon to achieve sufficient internal activity to actively eject water into surrounding space. It is substantially more probable that the majority of ocean-bearing moons resemble Mimas in their surface presentation. There could potentially exist dozens of stealth ocean worlds distributed throughout our solar system that have been systematically dismissed from serious consideration simply because their external appearance suggests geological death. Mimas delivers a crucial lesson to planetary exploration. The absence of observable surface activity does not constitute proof of an inactive or dead interior. The lack of surface manifestations merely indicates that the thermal insulation system is functioning with perfect efficiency. The most profoundly shocking detail concerning the hidden ocean within Mimas is not simply the fact that it exists at all. Rather, the truly astonishing revelation is that this ocean appears to be extraordinarily young in geological terms. Based on the sophisticated computer models employed to analyze the orbital mechanical data, planetary scientists estimate that this subsurface ocean likely formed only approximately 15 million years ago. Within the context of a solar system that has existed for 4.5 billion years, this time frame is effectively the immediate present. The implication suggests we are examining a world that has only recently awakened from billions of years of frozen dormancy. The primary evidence supporting this remarkably young age estimate derives from the preservation state of surface morphological features. Ice does not behave like solid rock over extended geological timescales. Across sufficiently long time periods, ice exhibits behavior characteristic of an extremely slow-moving viscous fluid, particularly when subjected to elevated temperatures. This deformation process is classified as viscous relaxation in planetary geology. If Mimas had possessed a warm liquid interior continuously for billions of years, that sustained internal heat would have progressively softened the overlying ice shell. Over geological time, gravitational forces would have naturally pulled down the elevated crater walls and filled in the deep basin depressions. The surface topography would have evolved to appear smooth, subdued, and muted. That smoothed appearance is categorically not what we observe on Mimas today. The Herschel crater remains geometrically sharp, morphologically jagged, and topographically deep. Its walls still rise approximately 5 kilometers in height, and its excavated floor still plunges 10 kilometers below the surrounding terrain. This structural configuration could only survive intact if the ice shell remained extremely cold, mechanically stiff, and structurally rigid for virtually the entire geological history of the Moon. The exceptional preservation of these violent impact scars proves conclusively that the interior existed in a frozen solid state when the impact events occurred and maintained that frozen condition for billions of subsequent years. The orbital dynamics data provides supporting evidence for this recent formation timeline. The tidal heating mechanism that powers and sustains the ocean derives from the eccentricity of the orbital path. However, this energy transfer process consumes orbital mechanical energy over time. Across timescales of hundreds of millions of years, the gravitational energy transfer typically acts to correct the orbital eccentricity, progressively dampening the oscillations and circularizing the orbital path. Once the orbit evolves into a perfectly circular configuration, the tidal heating mechanism ceases to operate. The ocean would then freeze solid in the absence of continued energy input. The observational fact that Mimas currently maintains a significantly eccentric orbit strongly suggests this gravitational interaction initiated relatively recently in geological terms. The system has not yet had sufficient time to consume that orbital mechanical energy and circularize the path toward equilibrium. This evidence pattern paints a picture of a solar system that continues to evolve dynamically rather than existing in static equilibrium. Mimas spent the vast majority of its existence, billions of years, as a frozen, geologically dead block of ice suspended in orbit. Then, in relatively recent geological history, some gravitational interaction likely perturbed it into this new eccentric orbital configuration. This orbital change ignited the tidal heating engine and ice began melting progressively from the interior outward. We find ourselves observing this moon at an extraordinarily rare and specific moment in its evolutionary life cycle. We are witnessing in real time the birth of an ocean world. The liquid water is very likely still expanding in volume, slowly eroding and melting away at the overlying ice ceiling. But the ocean has not persisted for sufficient duration to erase the ancient geological history that remains written on the surface. The reclassification of Mimas as an active ocean world represents one of the most significant paradigm shifts in planetary science that has occurred in the last decade. It forces the scientific community to abandon the comfortable assumption that we can accurately judge the internal state of a celestial body by examining its external cover. Throughout the entire history of space exploration, mission planners have prioritized investigation targets based predominantly on observable surface activity. We followed the cryovolcanic geysers and the tectonic fracture systems. The operating assumption held that if a world appeared dead on its surface, it was dead throughout its interior. Mimas has proven definitively that this investigative methodology contains fundamental flaws. A planetary body can present the appearance of a frozen, battered artifact from the early solar system, and simultaneously harbor the physical conditions necessary for life just a few dozen kilometers beneath the dusty, cratered surface. This discovery fundamentally breaks the traditional definition of the circumstellar habitable zone concept. Classical planetary science taught that liquid water requires a specific range of distances from a parent star to exist in stable form. We searched for the so-called Goldilocks region, where temperatures were neither too extreme in either direction. Mimas proves conclusively that gravitational tidal forces are equally capable of creating a habitable thermal environment as stellar radiation. It demonstrates that a world can generate its own internal heat in the freezing darkness of the outer solar system purely through orbital mechanical interactions. This revelation opens up the number of potentially habitable worlds significantly beyond previous estimates. It means we cannot limit our search exclusively to Earth-like planets orbiting within the traditional habitable zones of their stars. We must additionally examine any moon trapped in a gravitational tug-of-war between a massive planet and neighboring satellites. The implications of this discovery extend far beyond the Saturnian system. If Mimas successfully conceals a global subsurface ocean beneath such an unpromising exterior, then we must systematically question everything we believe we know about the other small icy moons we have previously written off as scientifically uninteresting. Satellites such as Uranus's Ariel or Miranda or Neptune's Proteus exist in fundamentally similar environmental conditions. They are small in size, extremely cold, and follow eccentric orbital paths. Until this discovery, we systematically ignored these bodies because their surfaces appear solid, ancient, and inactive. Now, based on the Mimas precedent, they must be considered prime candidates for harboring stealth subsurface oceans. We effectively have to return to our archives and recheck our preliminary assessments of dozens of objects we previously categorized as unremarkable space debris. This paradigm shift fundamentally changes how we must design future planetary exploration missions. A simple camera flyby observation is no longer sufficient to comprehensively survey a planetary system. To uncover the hidden truth about these bodies, we need to position spacecraft into sustained orbital configurations around these moons to measure their gravitational field variations and rotational libration patterns with high precision. We need to feel the subtle ways these bodies move, rather than simply photographing how they appear. We used to examine the solar system and perceive only a few rare oases of liquid water and potential life scattered amidst a vast desert of dead rock and ice. The reality that is emerging from discoveries like Mimas is likely dramatically different. We are beginning to understand that we exist in a system where liquid water is simply hidden from direct view rather than genuinely absent. The most heavily battered, quiet, and superficially unsuspecting objects visible in our telescopes are quite possibly the ones that are most geologically and potentially biologically alive in their deep interiors. Mimas should not be classified as an anomaly or an exceptional case. Instead, it likely represents the prototype template for an entire new class of living ocean worlds that we are only just beginning to recognize and understand. The implications for astrobiology are staggering in scope. If ocean worlds can exist in such complete camouflage, then the statistical probability of liquid water existing throughout our solar system increases by orders of magnitude. Every small icy moon in an eccentric orbit around a gas giant must now be considered a candidate location for liquid water. This doesn't simply double or triple our list of interesting targets. It potentially increases the number of ocean-bearing worlds in our solar system from a handful to potentially dozens. Each of these hidden oceans represents a completely isolated chemical laboratory where organic chemistry has been operating for potentially millions or billions of years. The water in these oceans is not stagnant. The tidal heating that keeps it liquid also drives circulation patterns. Heat rising from the rocky core would create convection currents similar to those in Earth's oceans. These currents would transport dissolved minerals and chemicals throughout the water column. If the rocky core contains hydrothermal vents similar to those found on Earth's ocean floors, these would provide concentrated sources of chemical energy and mineral nutrients. On Earth, hydrothermal vents support thriving ecosystems completely independent of sunlight. Life forms around these vents derive their energy from chemical reactions rather than photosynthesis. The same process could theoretically operate in the dark ocean of Mimas. The ingredients are all present: liquid water, chemical energy sources, dissolved minerals, and millions of years of stable conditions. Whether life has actually emerged in these hidden seas remains an open question, but the potential cannot be dismissed. The discovery of the Mimas Ocean also forces us to reconsider the timeline for ocean formation on other icy moons. If Mimas's ocean is truly only 15 million years old, then ocean formation on icy moons is not necessarily a primordial feature. These oceans can turn on and off based on orbital evolution. A moon might spend billions of years frozen solid, then suddenly develop an ocean when gravitational interactions push it into an eccentric orbit. This means that even moons we have already studied could potentially develop oceans in the future, or may have had oceans in the past that have since frozen. The history of water in the outer solar system is likely far more dynamic and complex than we previously imagined. Jupiter's moon Callisto, for example, shows some evidence of a possible subsurface ocean, but the evidence is ambiguous. Perhaps Callisto had a vigorous ocean in the past that is now in the process of freezing, or perhaps it is on the verge of developing one. The technology required to definitively detect these hidden oceans already exists. The method used to discover Mimas's ocean, measuring precise libration through long-term orbital observations, can be applied to any moon if we dedicate sufficient spacecraft time to the observation. Future missions to the outer solar system should prioritize these measurements. Rather than conducting brief flybys of dozens of moons, we may need to commit to extended orbital missions around individual moons of interest. The James Webb Space Telescope and other advanced observatories may also contribute. While they cannot directly detect subsurface oceans, they can identify chemical signatures in any material ejected from these moons. If tectonic activity on any of these worlds increases to the point where material vents to the surface, we could potentially analyze that material remotely. The search for stealth ocean worlds represents a new frontier in planetary exploration, one where the most exciting discoveries may lie beneath the most unpromising surfaces. Mimas has taught us that in planetary science, as in many fields, appearances can be profoundly deceiving. The future of ocean world exploration will require patience, precision, and a willingness to look beyond the surface. It will demand sophisticated instruments capable of detecting subtle gravitational variations and minute rotational wobbles. Most importantly, it will require abandoning our preconceptions about what an ocean world should look like. The universe, as Mimas has demonstrated, is far stranger and more wonderful than our assumptions allow. Hidden beneath ancient cratered surfaces, warmed by gravitational forces we are only beginning to understand, entire oceans may be waiting to be discovered throughout our solar system and beyond.